In this video, we're going to introduce the concept of pulse width modulation and talk about how it's used. Pulse width modulation is an idea of increasing and decreasing power to a system. Now, the question is, why would we want to increase or decrease the power to something? Well, for example, if you have a light and you want to dim the light, you have a motor, you want to speed it up, slow it down, you have a heater, you want to make it hotter or cool or less hot. All of those are done by changing the power that is delivered to the particular device. So for example, let's say, since this series of videos are all focused on microprocessor, I'm writing assembly code and programs to make those microprocessor do things. The idea here is, for example, you have a pin, one of your I/O pins, and you're driving driving something. And let's say you can start by putting let's say this is 0, and there is a DC voltage of 5 volts being put in here. So in this case, P, power delivered to the system, is going to be voltage times current. So the choices would be, well, if I want to change the power, I could change the voltage, or I can change the current. Both of those can be done, if it was a power supply and a human was there, you could turn the knob, but both of those are very expensive things to do. And so we want to find a different way to reduce the power than just simply changing the level of voltage or current. And the way folks have come up to make the very efficient way of reducing power is, instead of giving a DC voltage, which is all the time on, it's 100% power, what they decide to do is go ahead and, instead of turning it on all the time, turn it on for a period of time, let's call them T on, and then turn it off for a period, okay, and then turn it back on and turn it back off, and on and on. So instead of giving a DC voltage, they give it more or less a square wave for signal. The upper part is going to be 5 volt, the lower part is going to be 0 volt. But then if we call this whole thing a period, capital T represent the period, which, as you may know, this is 1 over frequency. T says how many seconds a single cycle takes. F says how many cycles exist in a second. Okay, so what does that do for us? Well, what it does is that by adjusting how long T on is, we actually are able to change the average voltage delivered, and therefore the average voltage for P. So for example, let's assume we set T on to 50% of the period. So half the time is on, half the time is off. And by the way, this signal is said at this point to have a 50% duty cycle. That's another word used to refer to this duty cycle. And that basically means that half the time is on, and that's it, 50% of the time is on. So in this particular case, what happens is that, as far as the power is concerned in this device, the power is the average of on time and off time across the board. So instead of seeing 5 volts, it's gonna be seeing 2.5 volts, half as much, okay? And therefore it's gonna see half the power. So in this case, we're gonna have 50% power, okay? Let's carry this one more example and be more specific to get a little bit of a sense. So let's say we have a signal, instead of being on all the time, we have a signal which is on so it's a 25% on, or what we call 25% duty cycle, and then that the off time is 75% of the time, and then it comes back and repeats itself again. So in this case, then the period would be, let's say the period for this thing is set to be 10 millisecond, okay? Which basically means then 2.5 milliseconds is on, and then 7.5 millisecond is off, okay? So in this case, we are delivering 25% power to our system, okay? Now, that makes it very nice because I can simply use the timer. In the previous videos, we talked about the timer, so I can turn my timer on and have it on for a period of a time, and then depending on what duty cycle I want. So if I want it to be 10% duty cycle, I'd turn it on for 10% of the period and turn it off the rest of the time, and I get 10% of the power. And then for this one, you can kind of see all the numbers. The period is 10. So let's finish this up. And then the frequency of this would be 1/10 millisecond, which is 10 to the minus 3 seconds. Therefore, this is 100 cycles per second, or sometimes referred to as 100 hertz. Okay, so that's we know the frequency now, we know the period, we know the duty cycle. If I was to run a DC all the time, I would get 100%, and as I reduce the on time, I reduce the power delivered to that. Now, you say, doesn't the device we're connected to see that is turned on and is turned off? The answer is yes and no. For example, if you're talking about a light, human eye, once you get above about 30 hertz, 30 times per second, once the frequency goes above 30 hertz, your eye will integrate it together, and you see as if the light is on all the time, except a little dimmer. And as you increase the duty cycle, it gets brighter. So as long as your frequency is above that, your eye will integrate it in a time. We like to keep this around 60, even though 30 does. Anything above 60, it might give you a little bit of a headache because your subconscious still see it, but your conscious doesn't. So usually we keep it around 50, 60 hertz or higher, just for human thing. And then the other one is motors. Now motors are kind of, if you want to think about it, a lot slower in responding because they have a lot of electromagnetic things in them, like a capacitance and inductance. So you can run the frequency as low as 20 hertz and the motor would not know that the power went away. So as long as, and then by changing the on time, you make it go faster or slower. Electric cars run this way, the fan runs this way, all of those devices do that. And then the last one, which is the slowest of all, is a heater. If you have a heater and you want to basically reduce the heat that comes out of it, all you have to do is change the duty cycle. And in this one, the heaters are really simple because of the frequency. Frequency can be as low as like 1/10 of a hertz, or actually more than 1/1000th of a hertz. And I don't think you will be able to tell the difference, or even lower. I'm not this one, because things take a long time for them to cool down, a long time to heat them up. You can even actually look at your stove. If you have an electric stove, if you set it to low, you notice the electric stove shuts off and turns on, and that's how it modulates. If you put it in high, it's on all the time. If you put it on low, it's modulating. It's doing pulse width modulation, but the pulse width modulations are like in minutes, not in seconds. Okay? So that's a couple of examples for you to consider as far as how pulse width modulation is going to use. In the remaining videos, we're going to use pulse width modulation for mostly designed for motors, and we use to pick micro pins, have different duty cycles, and you can connect those to motors, lights, whatever it is that you want to do. Most of the time for our experimentation, we're thinking of motors, but they will look for a wide variety of signals as well. That brings us to the end. As a quick summary of this, then, you can pick a signal. The only thing you got to make sure, you have to know what you're driving to make sure your frequency is high enough. In other words, the period is short enough such that it gets integrated and the device sees it as an average power as opposed to a turn on, turn off. And as we mentioned, lights, motors, heaters, they have different requirements as far as how fast you should be running this thing. And then simply by increasing or decreasing the on time or the duty cycle, you control how much power is delivered to the system. In the next few videos that we have, a couple videos we're going to see how PIC Micro 18F1220 has a single built-in pulse width modulator. We can see how to configure that. And then more exciting, I think, is the next video we have. We're going to talk about how to use timers we've learned about so we can make as many pulse width modulators as we like.